Thanks a lot for the presentation. First of all, I want to give thanks to the people of the University of Seville for this opportunity to participate in his workshop, in this very interesting workshop related to microgrids. In my case, in my presentation, I'm going to go deeper at the converter level with the control of the system, and I'm going to explain how the roles of the converter in the grid, and how this converter is able to be integrated in a microgrid. This schedule that I get, I'm going to pass through some concepts, definitions of microgrids. I will use the perfect concepts that previously has been explained in the previous presentation, so I will not stay so much time. In that way, I will be able to fix my presentation to the hour. Later, I'm going to explain the main roles of the microgrid converters as passing through the grid feeding, grid forming, and grid supported converter. Later on, I'm going to make an introduction of the synchronous power in the microgrids. I'm not going to. I make some modification during the presentation. So the chapter 4 I eliminated. So the concepts that I was explaining in that chapter 4 was probably well introduced by the previous presentations. And I'm going to talk next with the synchronous service in the microgrids. So going as to make some introduction of the microgrids, this concept of the microgrid with a soap of different distributed generation elements that all of them should be able to work in a coordinated way. Previously, the old-fashioned we get a centralized generation where we get a generation point in some point of the grid, and the opposite point we get the consumption. Now all of these elements are mixed, and now we get the generation close to the consumption. Now we get consumers, prosumers. Now we get ancillary service. This is all of that mix of concepts that help to the microgrid work in a more stable way. But all of that concepts should work in a coordinated and a controlled way. Different concept of microgrids, it's called that they should work with that loads, that generation systems, synchronous generators. Also we get energy storage elements. Also we can find the prosumer there. And all of that system should be able to work as a grid-connected way as in an isolated way. But the microgrid concept, the microgrid opportunity is that this piece of this area or this area of the grid should not only be able to work in a stable way by itself, also should collaborate with the microgrids that there are next to that. This is the main opportunity of the microgrid. Just this grid supporting collaboration between the grids or the microgrids or the areas that there are next to them. The requirements of the microgrids, well, we have to allow bidirectional power flows. We have to get reactive power control. Also, we have to allocate redundancy. Also, we have to get a space for integration of non-conventional generation, like that ones that have been largely talking today. These photovoltaics, this wind energy system. We have to work in an optimized way, especially the non-renewable. That are the most costly. We have to get a space for integration as a short, medium, and long-term energy storage, as has been introduced previously. Also, we have to allow modularity. We have to be able to survive to short circuit conditions Also, we have to allocate power rate limits. Also, the system should be fault tolerant, and should be work as a plug and play system. Okay, should be able to allow the high penetration of distribution generation without a reconfiguration of the full macrogrid. Okay, for all of that requirements, each time the standards and the rules has been more exigent. Okay, first, initially, in front of any fault, the requirement was unplug. Okay, if you get any short circuit, the PV or the wind system should be unplugged, should be turned it off. Okay. Firstly, the distributor and the transmission operators see the potential of the wind turbines to work against the fault, okay? And low voltage right through was a requirement, also the high voltage right through, okay? And actually, in the recent standards was the IEEE and the UL, the American standards for give a guideline for microgrids with a standalone capability, okay? That microgrids should be able to work in a standalone mode and should be able to be switch from one state to the other one, okay? And with the new procurements or permit should requires to get a new ancillary service like inertia emulation, like reserve and other of the other of the elements to allow a more flexibility grid. Okay? I will not enter to the topology level because I will not go so down to the IGBT level. Okay? Don't worry about that. The power requirements of the converters, it should be work in a range between 220 until 300 kilowatts. The voltage level should work in between that levels, okay, between 230 kilowatts. And actually, most of them it's working at low voltage, but each time to get a more efficiency and to allow the microgrid to cover a bigger surface, so the voltage level is increasing, okay, it's working with a high levels. Until now, the switching frequency has been something close to 10 kilohertz, but as the technology of the switches is evolving, this switching frequency is going to move at 50 kilohertz. Okay? In that way, we are going to get more efficient conversion systems. The control requirements. Well, the control requirement for the converter will be to allow active strategies for MPPT. We have to allow delta strategies, permutation. The converter should get be able to work in a grid-connected or island mode, as well has been well solved the transition operation between different models. Okay, should be able to allocate the droop control, because until now has been the more standard and a more fast solution to maintain the microgrid in equilibrium point. Okay, at least is the last reserve, and also it should be the capability of modification of that droop curves. Okay, for a higher control system, a secondary or a tertiary control that previously has been very well defined by Professor Rodrigo. And also they have to get the capability to receive external reference of PQ, voltage, or frequency from the microgrid central controller. Okay? Which are the roles of the microgrid power converters? But mainly are three roles. Okay? It's the grid feeding, the grid supporting, and the grid forming one. Mainly the grid feeding are those ones that are the most standard, or most standard, or at least the most implemented. Okay? Because it's basic mainly are the MPPT algorithm. Okay, it's the matter of to inject as much power as I able to do that. Okay, this has been a problem until now. Okay, this is one of the problems of the renewables, that they are only working as a feed the grid, And the problem is when there are not the primary reserve. Okay, they are not the available of the primary energy. So in that way, they are starting to enter the grid supporting converters. Okay, the grid supporting totally or partially adjusts its operating point function of the condition of the microgrid or the grid. Okay, so if the system is working under frequency, so the grid supporting converter injects more power in order to accelerate the grid and restore to its original point. Okay, and the same for the reactive power. Okay, later on there also get the grid forming converter. Okay, the grid forming converter, it's in a popular way, it's the UPS. Okay, it's that system that it's working in island mode like the UPS. The UPS is when it's not able to work with the grid at the same time. Okay, you get one or you get the other one. Okay, so the grid forming is exactly the same. Okay, you get the grid forming. It's generating constructing the voltage. It's imposing the sinusoidal voltage as in amplitude, as in frequency, as in phase. Okay, so these are the main three roles. I'm going to go in more detail of that one. The grid feeding one are those ones that, as I explained, it's based on a constant power injection, or constant power, or maximum power point tracking, okay, and give to the converter a reference current function of the P and Q. And this P and Q reference is given by an MPPT algorithm or by the secondary control. Okay? And this is one of the main roles of the converters that actually are connected to the grid. This system cannot work alone without a grid former or without the grid connection itself. Okay? It's not able to supply a load without some element that impose the voltage sinusoidal. Okay? And also one of the biggest advantages of that system, it's able to easily can be parallelized without any type of communication without other elements. Okay? The deepest, if you go in more detail, okay, we can find different blocks. Sorry, this is not so much detailed. We get the power control loop, okay, from where we find the reference of current. This reference of current enters to a PI, okay, and that PI finally gives the reference that the system, that the converter should to follow in order to supply some specific power. Okay? Then it's very important for this type of converters to get a very good PLL. Okay? The PLL, the phase loop. Okay? This is a synchronization system. In that type of converters, the synchronization system is fundamental. Okay? This is a basic structure. Okay? It's a synchronous reference frame PLL. But there are more complex and more effective, okay, like the SOGIs, like the dual SOGIs, the FLL, or other ones, okay, that will give you a better response. But this is just to get a clear idea what they are inside, okay? What else? This is the grid feeding. Also, this is previously I showed with the DQ with the rotatory reference frame. This is with a stationary. It's with alpha beta elements. Okay, it's exactly the same topology, but translated to alpha beta. It's exactly the same, the performance, and we calculate from the currents. We calculate the active and reactive power. This active or reactive power is translated to obtain some reference, current reference, and this current reference passes through a proportional resonance controller. Okay, in order to give the voltage reference to control the power converter, the switches of the power converter as a grid feeding element. Okay, there the most important element of that part is that synchronization element. That in this case I showed the structure, taking the advantage that I'm working in a stationary rotatory frame, okay, in alpha beta. This is the synchronization element. Okay, this is a frequency loop SOGI. Okay, this element has proved a lot of advantage, but we are not to enter in so much detail. Okay, later we get the grid forming ones. The grid forming converters are these ones that it's a voltage control system that impose a frequency, impose a amplitude, and from that frequency, that amplitude generates a sinusoidal by the mathematical equation. Okay, and from that, the system, the equivalent representation is a voltage source that in series with an impedance. Okay, and this frequency and voltage amplitude can be given by some constant. For example, that you get storage in case that you work alone in a system, or maybe can give to the converter by a secondary control system. Okay. Also, if that this grid forming converter it's able to work only in island mode. Okay. Because we cannot get a voltage source. Two voltage source connected between them, because it's a very unstable condition, unless that this impedance is big enough, okay, to maintain some stability. If this impedance is very small, you are going to get a lot of problems with stability. Okay. If, for example, this grid forming power converter is being used to a microgrid to allow to pass from island to a grid connected mode to island one. In that moment, that make a transition of one operation modes, one of the converters should assume the role of the grid forming and impose a voltage for the rest of the grid feeding converters. Okay. Once the grid is restored again, or once the microgrid central controller wants to connect again to the grid, so the both elements should be synchronized, resynchronized again. And we can give, the central controller can give, observing the two voltage, will give a delta E and delta of frequency in order of omega to make the resynchronization and the connection again to the main controller. In that moment, that converter immediately should pass again to work as a grid feeding converter. Okay? This is the structure. I will pass because if not, I'm going to spend so much time in that. Okay? It's the voltage controller, give a current reference, and then we get a controller. This is the same structure of the island mode. But the grid forming mode, okay, but in this case in alpha beta, so we get the resonant controllers, okay, and this is the voltage and the frequency in that concept is being imposed by some variable storage, but as I say, this variable can come from a higher control level, okay. Also, we get the grid supporting converters. The grid supporting converters, as being explained, is based on the Drup converter and can be formed from can be composed or the control structure can be coming from the grid feeding one. It's the most typical, okay, where we get a power and Q reference, and this P and Q reference can be modified in case that in case of the Drup equations. What we get there is the Drup equations. Okay, if we get some modification from the reference frequency or from the reference voltage level, we are going to give an extra P or extra Q, can be positive or negative, okay, in order to restore again the grid conditions again in its operation level. Also, we can get this system can be developed from the grid forming role converter. What is that idea? So it's mainly the same, but finally what I get is that instead of to get a control source, a current control source, I'm going to get a voltage control source. Okay, in that system, the as the system give the frequency and the frequency of the grid, it's give the amplitude of the grid, and that values are being modified according with a group functions between the reference and P and Q curves that's coming from a higher level system. Okay? As I explained, the system, as the voltage source, it's 2 voltage source are very unstable system unless that we get a significant impedance there. Okay? These are the control structure of the grid feeding converters. It's exactly the same. That one. This is the control structure of the grid supporting converters based on the grid feeding. Okay, is exactly the previous one, but now the power reference is constructed from the Drup equations. The same occurs with the grid supporting power converters based on the grid forming structure. Okay, in that way, we are going to introduce the concept of the virtual impedance. Okay, as explained, this system it's unstable. This system is unstable unless a significant impedance is being in the middle between the two sources. Okay, usually, or not always, but usually the grid impedance it's in case of strong grids. The grid impedance is very small, so to avoid that, what we do is in control add a virtual element that we can modify. We add an impedance, a virtual impedance. Okay, this impedance it's only inside of the control. Okay, it's inside of the DSP of that it's controlling the converter. Okay, the peak, and that impedance give the voltage level to the voltage control loop. Okay, and this voltage control loop gives the reference to the current control loop. The Drup curves, as you know perfectly. Okay, this is concept that is coming from the machines. Okay, so from the synchronous machines, and the synchronous machines it's able to operate are able to easily can be parallelized thanks to that Drup curves. Okay, each converter, as each machine, gets its own Drup curves. That when the grid is working at some specific frequency, impose or shares determines how much power should give each one of the converters. Okay, as the synchronous machines does, in the same way. If we get a change with the power, if we get a change of the impedance of the microgrid, a new point is going to be determined according with that curves. Okay, and the sharing of the power is going to be performed with that Drup curves. Okay, so this Drup usually we get as we read. We get a relationship between the power and the frequency, and the active power and the frequency, and also a reactive power and the voltage level of the microgrid. Okay, but this it's because usually, not always, the microgrid gets a role as in an inductive line. Okay, but what happens in the low voltage grid? The low voltage grid, the role of the line, it's more resistive. Okay, and we can go to some levels until this line is so much resistive that we get the crossing effect. So the power, if we inject more or less power, what we are modifying is not the frequency. So it's the voltage of the microgrid. Okay, and we can go also to the extreme that if we inject or absorb more or less reactive power, what we are modifying is the frequency of the microgrid. Okay, so as we saw, there is a large dependence between the Drup curves and the line impedance. Okay, and what happens if we are in a half in a resistive character or an inductive line. Okay, so it's very important to know exactly the grid impedance. Okay, and this is a problem because the grid impedance is changed. Okay, it's automatically changing when the one load is connected, when there is one fault at some point, when there is another fault in another point. Okay, so this what the previous concept that I was explaining to the virtual impedance. So instead to work with a real impedance, I'm going to impose some character of that. I'm going to impose a series resistance, okay, that I'm going to decide by myself which is the value of R and L. And I'm going to impose some character of the microgrid. Okay? Come back to the reality, not to the virtual. Come back to the real. Okay? This is the explanation that I will explain very fast. Okay? This is the power equations that define the power transfer between two voltage sources. Okay? Function of the voltage level, function of the impedance. And if we are working on the inductive line impedance, we are going to suppose that we get that relationship between the frequency and the active power. And if we are working with the inductive line equation, we are going to get a relationship between the voltage and the reactive power. And this will be the droops. Okay? As the same way that it was explained previously, that droops will define some operation point of the microgrid. And there, the secondary control will come and you say, okay, the new equilibrium point that you find, it's not the one that I want deciding, and I want to restore again the frequency of the microgrid. So what the secondary control does is to move that constant, okay, of the droop equations to move the equilibrium point from that point to this one. Okay, impose a new equilibrium point at some specific frequency. The same occurs with a resistive line, okay, but in opposite way. The resistive one, the reactive power is related with the frequency, the voltage is related with the active power. And the droop lines change, okay? This is why, so finally, you get a lot of problems with the implemented with the droop if you don't know the line impedance, okay? True is that there are a lot of algorithms in the literature trying to find or making active elements to find that impedance, okay? But in some cases, that active elements to detect the line impedance are being in problems with them when at the same time two converters are trying to find the grid line impedance. So finally, we get advantages and disadvantages of the droop curves. Okay, the droop curves is a very effective solution to regulate the voltage magnitude in medium voltage networks. Medium voltage because it's the inductive line it's imposing. The problem is that it's highly dependent of the Rx ratio. Okay. So the advantage is that it's not necessary any communication channel to apply some equilibrium point. It's very good, okay? Don't depend of the communications, at least to get the primary point, working operating point. The trade-off is that you need a sophisticated grid impedance estimation algorithm, okay? Another advantage is this system is largely developed in power system, because this is the communication, this is how the transmission operated until some years has been talking with machines, okay? And the problem is that there will be a small mismatching in the grid impedance estimation, especially when we are trying to work with power converters and with its sharing of harmonics, okay? That also is a problem of the grids, and especially in the macrogrids. So this is where the virtual output impedance is making the strongest. Okay, we can impose a line. We can impose the character of the line. we can say that a resistive line works or performs like an inductive one. Okay. In one point, this is the control strategy how the virtual impedance is working. Okay. This virtual impedance from the Greek current multiplied by the virtual impedance impose a voltage that it's subtracted from the Drup equations. This voltage final reference moves to a voltage loop, and this voltage loop generates the current reference to the current reference loop. Okay. After that, first of all, sorry, because I was thinking maybe not so biggest TV, but with a usual projector, and I was thinking with a large screen. Okay. So the virtual impedance gets some benefits over some of the drawbacks of the Drup control, and these benefits are related to the overall system. It's more damped. It's this virtual impedance. It's able to provide automatic harmonic current sharing. Okay, something that the Drup equation is not able to do, and the phase error have a very low effect in the power sharing. Okay, because now we have decoupled the P and Q Drups from the real line impedance. This is why we move to a concept, or we introduce the concept that is called the synchronous power conversion. Then this tool is very important. It's very strong in microgrids environment. What is that? Okay, we get two voltage source, we get a line impedance with them, and the power sharing it's imposed by the LR. In these LR elements, we get the real one plus the virtual ones. Okay. But we detect that there is some problem. Which is the problem? Is that when you are implemented the equation, okay, you get your current, you get your voltage control, okay, and the thing is that you get a derivative term there, okay, and derivatives there are very unstable in front of a fast changes with the voltage. We get a noise problem with the sensors, okay, so it's not good to add filters to the sensors. And so to avoid that problem situation, we develop a new concept that is called the virtual admittance. Sorry, this is an error. Okay, it's the virtual admittance. Okay, not the virtual impedance, it's the virtual admittance. What is the advantage? We sense the voltage in comparing with some, and now I'm going to explain from its coming, and we are going to compare it from another voltage. We pass through that virtual admittance block, okay, and from that we generate the current reference. Okay, in that way we avoid to get derivative term. In that way we get a current controller. In the previous case, we're getting this an error in the symbol. Sorry, this should be a sinusoidal voltage. In the previous case, we get a voltage control that in some case can get some problems with stability. In that case, with the virtual admittance, we get a current source, and the current source doesn't get so much problems with stability issues. Okay, also they get, but less that if compared with the voltage. Okay, this is the implementation of the synchronous power conversion. As you can see, this concept, it's just a control concept, so we don't have to change, to modify in any way the topology, the power topology of the converter. It's exactly the same that you get with your control. What we do is to impose a voltage, comparing with a real voltage, and this voltage difference pass through the virtual admittance. And this virtual admittance gives a reference, we give a current reference. And this current reference will enter in the reference of the power converter that you can buy to any supplier. Okay? This is the reference that you are going to give to your power converter supplier. The advantage is the value of the RL can be adjusted to have a friendly interaction with the grid. Okay? in function of how the grid is working, how the macrogrid is working with this situation, if it is grid connected, if it is working standalone, you can determine which impedance you want, which character you want. Okay? I'm going to explain, for example, some simulations. So this is some simulations that we've done with that tool, okay, with the virtual impedance tool, and you can see if how modifying E, this voltage reference, we can say to the grid, okay, inject reactive current or inject active power, okay, just to determine some value with the E, okay. Also, we can make it change with the admittance value, okay, and we can inject some. There are no values. It's only the simulation only from the qualitative point of view, okay. We can get active and reactive power being injected to the grid, and modifying the virtual admittance, we can modify the value that we want to inject to the grid, okay. As I say, this system, okay, can permit to set a dominant inductive behavior also in low voltage lines, okay. This is an advantage. Permits easily a regulation of the power sharing between converters, because now the power sharing of the converter is going to be determined with the output virtual admittance, okay, like in the same way like the synchronous generator. And also, as this system virtual admittance is imposed by an integration, this contributes to reject distortion in the grid, okay. And as we are emulating in so much the performance of the synchronous generator, why not emulate also the electromechanical model of the swing equations? Okay, so let's go to do that. Okay, we go to the next step to emulate the swing equations of the synchronous generator. Remember that we are talking about power converters. Okay. Okay, so this is the typical swing equation with inertia, with the damping. Okay, the damping of the synchronous machine, it's a trade-off with two elements, because the damping windings are losses. It's a losses in the system, but are necessary. Okay, are necessary in order for the machine to get a damped response. Okay, now this damping parameter. This is a very superficial definition, okay? Don't be so much specific. This damping, now you get as a constant in your code, okay? And this constant in your code, you can define the value that you want. So finally, if your system, if your converter, you get oscillations with the power that is being injected to the grid, change online that damping constant or damping variable, okay? In order that you can impose the system response as damped as you want, as the secondary control imposed, as the microgrid central control imposed, okay? These are the equations that define the system, performance, okay? Related with a power that it's in. This P out, it's a power that the converter is injecting to the grid. That P in, it's the power that it's not the input power. Okay, this is not losses. This input power is the imaginary synchronous power. Okay, that theoretical the converter should inject to the grid. Okay. This is the full implementation of the SPC. As with the electromechanical block, that will be the part. It's that part, okay? This is the slide this is the previous slide, okay? The previous slide gives us a frequency amplitude. Sorry, give a frequency. The amplitude is given. The amplitude is given by a pi from the Q difference, delta Q, okay? And this passes from a voltage control oscillator. This is a very easy block. We get a frequency, get an amplitude, so multiplied by the sinus. sinus plus 2p over 3, and sinus of the frequency of 2p minus 2p over 3. Okay? And finally, we are going to get E, and this is the E that we are using. This is the E that we are using as an input of the virtual admittance block. So this E is imposed by a drop frequency of the required frequency or the required voltage amplitude, or this block is optional. This is the drop, or this E is imposed by some P and some Q imposed by an external controller, like the microread controller. Okay, central microread controller. You can go to the level that you want. Okay. Okay. So let's go to explain some of the service. Okay, there is a point that I skip because this is the point where the primary, secondary, and tertiary control was defined. But to be in time, I prefer to get the better definitions that the previous presenter give. Okay, this is again the problems with the distributed generation with a lot of elements. And let's go to pass to what the SPC is able to do inside of a microread. Okay, inside of an stable microread. The first of that, this is not so fancy. This is the typical to maintain the microread working in a continuous operation mode. This is the window framework that the microread should work, and the SPC should provide active and reactive power in the same way like other converters does. Okay, but at the moment it's not so much. This is the drop. Okay, the typical drop with its dead band. Okay, to define the operation point of each one of the SPC in order to maintain the microread in stable conditions. What is able to do the SPC? The SPC is able to inject reactive power in front of a voltage sag. In that way, when the voltage sag is following the grid code requirements, okay, the SPC in front of a voltage sag injects the specific reactive power in order to maintain the voltage, in order to support to the voltage restoration level. Okay, the good thing is that you don't have to change your control. Any variable should change when a voltage sag is being detected. The same structure that I showed previously, it's able to give or to support the voltage, low voltage right-through requirements without any external condition, without any new control or new layer of control. Okay, it's able to do it like in the same way like a synchronous generator. Okay. The previous one was simulation, and now I'm going to start to share you a set of experimental results that we develop. Okay. Again, sorry for the size of the draws and the simulation. Okay. As I explained, the SPC is able to perform the performance of a synchronous generator. In that system, what we did is we get two SPC working against of a low voltage right-through condition. Okay, working against of a voltage sag. Each of that converter is emulating a machine, in that case of SPC of a machine of 100 kilowatts, and in the green lines, in the green waveforms, okay, the SPC was emulating a machine of 50 kilowatts. And both converters, without any modification of the control structure, it's able to, from the initial voltage sag, it's able to give enough reactive current power in order to restore and try to elevate as much as possible the voltage level. Okay? So in that case, the system, instead of to arrive to a voltage level of 100, it's able to be in the voltage level of 250. Okay? Something like close that. The good thing, I explained, I will say it again. The good thing is that this is able to do that without any change, without any change in the control system. The same it's able to do with inertia. Okay, the power converter is able to emulate inertia, and this is another of the new requirements for the new standards that is going to come. This is the filtered frequency of the grid. Okay, it's passing from a deep band, and this we get the age of the inertia that we want to emulate. Okay, this age, it's for the requirement, it should be between 0 and 15 seconds. And the good thing of the SPC is that inertia is able to be changed. You can change online the H value, okay, or the J value. We can change that value. Why it's necessary to change? For example, imagine to start a big generator. Takes a lot of time. We have to spend so much time to start a new converter? No. At that point, we can make the inertia in a very small value, okay, in order to fastly start up the equivalent machine. And in some cases, it's interesting that that inertia gets a big value in order to provide large peak of power. Okay? This will be, as is assumed, this will be a function of the power that you get on the reserve, okay, from the primary source. Instead, if you get a PV panel, you are going to provide inertia just in one direction, okay? But if that PV panel supports with batteries, you are going to be able to provide inertia in both directions, okay? Also, with the PV panels, if you get some reserve, you are going to provide inertia in both directions. Okay, like taking that reserve as a energy storage. Finally, it's a trade-off. Okay, this is experiment results. Okay, we make a frequency from us with this in that environment. We get a synchronous generator that it's working the point of common coupling with an SPC converter, with providing that inertia emulation service, okay? And we apply a constant frequency deviation, and as a result, the SPC gives a certain quantity, well, in that case, absorb a specific quantity of energy in order to restore the frequency again in its nominal point, okay? As we can change, as I say, we can change that inertia, okay? That inertia, we can say that's a 3, as 1.5, okay? If this inertia is different, we get a lack of another there, we should get another curves, okay? Sorry, it's being erased, I don't know why. We have to get the dark orange. It should get a big oscillation, okay? Because if the inertia is minor, the frequency variation will be larger, and finally arriving at the same point, okay? This is a problem that we get. So when in that island condition of the synchronous generator and the SPC, okay, and the SPC is working or it's generating when a new load is connected. Okay, to prove also this inertia emulation, we make, okay, let's go to make a simulation test. What happens when we don't get the SPC and we activate, we make a load change, okay? We get the previous slide, sorry, we are going to get the synchronous generator, and this converter will be a grid feeding one, okay? Okay. And we make a change with a load. What is going to pass? The grid feeding will remain constant, giving that power. Okay. So all the extra power should be injected by the by the synchronous generator. Okay, this is a very interesting simulation. Why? Look, when the synchronous generator gives the extra power, we are going to obtain as a result oscillation in the frequency. This is what is happening with the grid now. Okay, by the moment, most of the converters are grid feedings. And what is happening with the grid as the load is changing? That again we get more and more and more grid frequency oscillation. And this is a very real problem of the real grids, of the big grids. Imagine that problem with the microgrids. Okay, so where we don't get so much inertia. This is why we are emulating the inertia. Okay, to maintain again. Can show with the SPC results to maintain the inertial response that it was decided. Okay, and this is what we are working on. The same we can do with a power damping. It's a direct consequence of the previous one. Okay, to go faster, I will skip that slides because it's exactly the same. Okay, if with the SPC we can get a more damped response. And this damping can be imposed by ourselves or by a higher control level. Okay? This is another of the requirements of the microgrids to work in island condition. Okay? I'm going to show you some results in a microgrid where we get a larger experimental image taken from the oscilloscope. In the first part, we get the voltage. Okay? In the second one, we get on converter working as grid feeding. And in the last one, we get another converter working with as a SPC condition. We make a transient in that point. Okay, this is the zoom. We can see that this transient was the disconnection of the main grid. Okay, the SPC immediately after that small transient that it's difficult to see, not because the image is small, because the transient was very small. Okay. We get after some very small transient, the SPC converter inject the necessary P and Q to restore again the voltage. Okay, and we get again this is the case when the main grid is restored again. Okay. We add a delta of frequency and we add a delta of amplitude to the SPC in order to be synchronized again. And we can close the switch and there's not going to get any problem. Okay? This is very different from the typical converters because when we are making that closing of the main switch, automatically the grid forming should change to grid feeding system. You are going to get a transient when you are not going to be exactly control that situation. And it will be you can get any stable conditions. This is not a problem with SPC. Okay? It's not a problem because it's the same control structure. And you are not going to inject extra power to the grid. Okay? In that point, we just get a small variation of power a small extra power that doesn't affect the voltage levels, okay? Because it's so small that it's not being altered. This is another of the requirements of the SPC, okay? The black star capability. Okay, we are able to start from 0. Okay, this is the voltage of the point of common coupling. Start from 0 until to get a stable voltage. Okay, we get that noisy performance. Why? Because we are feeding the transformer energy, the unbalanced transformer energy that was supplying to the rest of the converters. Okay, the load was unbalanced transformer. This is why we get unbalanced current. Okay. Also there we are able to generate a black star mode. Also we get the problem of harmonics, okay, that's being affected the microgrid. I will go fast because I'm taking a lot of time. Okay, how we are going to solve that? We are going to add, harmonic detections. We are going to add that harmonic frequencies at the harmonics that we are going to solve. Okay, of course, in that point we are able to solve the positive, the negative sequence in case of unbalanced load conditions, in case of unbalanced sag conditions. Okay. Also, we impose the fifth harmonic, the seventh. In some cases, probably not, we are able to arrive until the 11th. Of course, we get the limit of the bandpass of the LCL filter, of the LC, of the line, of the grid connection line filter that you get. Okay, this is a maximum frequency that you are allowed to compensate. This is the case of this is the simulation case of the connection of a capacitor when the grid is distorted, and this is the same results, okay, with the SPC. But let's go to jump to the experimental ones that I prefer. I like it more. This is the both. This is, let me to start from the left. This is the unbalance. Sorry, this is a perturbed voltage due to a large harmonic load, okay, without the supporting of the inverter. We activate the SPC with the different admittance at different harmonic conditions. This is the voltage that we are going to get. Okay? And supplying the same load. We are able to restore again, we are able to detect the harmonic voltage in order to maintain the system again in its operation conditions. This is the unbalance. This is the same in case of unbalanced sag or load. Okay, this is when you get a short circuit external in a remote point. Your voltage distorted in the point of common coupling of your converter will be something like that. And with the introduction of the SPC, we are able to restore, or at least to reduce a lot the negative sequence of your voltage. Okay, if you get more converters will be work against of that negative sequence without any type of synchronization with them, without any type of high speed or neither low speed communication. Why? Because will be the negative sequence impedance who determine the power that each converter should give. Again, we get experimental results. Okay, we get an unbalanced sag, and the system, you can see this is the large transient, and this is the stable voltage. And then in that stable voltage, we make, between that 2 points, we make the unbalanced condition. Okay, we make a short circuit one of the lines. The system, in that case, because the grid impedance was big enough, our converter, each one is different power, was able to restore again the voltage conditions. So finally, the point of common coupling that it's supplying our loads, again is looking at sinusoidal waveforms. Okay, balanced sinusoidal waveforms. Okay, as conclusions, to finish more or less on time, we make a presentation of the power converters, of the power electronics converters, the techniques, and we take the advantage and we observe, the advantage and disadvantage of the Druck curves. Okay, this was a very powerful technique to parallelize inverter, but get some drawbacks. Okay, these drawbacks it's being solved with the virtual impedance. But that virtual impedance also gets some problems that it's solved with the virtual admittance. Okay? And also the virtual admittance is able to solve the nonlinear problems. It's able to solve harmonics. It's able to be in sharing, easily parallelized between the converters. And also we introduce emulating also the swing equation of the synchronous machine to emulate the damping, the inertia. We have been easy well, it's the SPC, it's easily parallelized. The SPC is able to be integrated in a 2 kilowatts converter until a 2 megawatts converter. There's no problem with the power that is managing, okay? The SPC also get the advantage to improve its advantage if the primary source gets some reserve. Okay, could be some electrochemical storage or another type of storage. Okay, also could be a reserve from the primary. Okay, the SPC also get one of the powerful tools of the SPC. It's that talks the same language of the transmission system operator. Okay, its commands that receive are P, Q, B, and frequency reference. Okay, as the system operator is usually it's used to do. Okay. Also, the SPC helps to stabilize the grid in from deviation, voltage sags, and balance faults or loads. Okay, harmonics and other quality issues. Also, the SPC is able to perform against the black star capability, Islam mode, resynchronization process, damping of power oscillations. It's able to introduce inertia emulation. It's one of the requirements. Okay. I don't want to finish the presentation without take a look of the experimental photos where we are performing the systems, the proof. Okay, this is the main grid, and this is the weak grid where we are applying all of that strange perturbation situations, and this is where the two inverters through the isolation transformer are injecting the necessary PQ in order to restore PQ and harmonic power in order to restore again the weak grid conditions. Okay, so thanks a lot for your attention, and I hope that I don't worry so much.